Okay, greetings everyone. Welcome to Photonics for Quantum 2. Good morning, good afternoon, good evening, wherever you are. We have an exciting talk today, and we have a full slate this week, in fact. We don't have a sponsored talk, so we have the main talk today, followed by a poster presentation. I'll remind you to take a look at the program schedule on the PFQ2 website, and there you can also click on the speaker drop-down boxes and access videos and slides for talks that have already been given. So I want to thank our generous sponsors whose logos you see surrounding me. I'll try to make myself a little smaller so you can see all the logos. And due to their generous contributions, we're able to deliver this content free of charge to you. So without further ado, I introduce to you Eric Fossum of Dartmouth College. Eric, take it away.
Okay, great. So hopefully you can all hear me and I'm not just talking to myself.
But we can hear you and we can see the slides.
Okay, perfect. Yeah, so I'm speaking to you from the shores of lovely Lake Winnipesaukee in New Hampshire, and happy to present some information about the quantum image sensor technology that we've been developing for a few years. First question is, what's new lately? And the answer is, the answer is that we're stuck. Why is that? There we go. Yeah, not much progress since the single photon workshop that was held in Milan just a month or two or a couple months before the stuff hit the fan in Italy. And of course, as everybody knows, most university stuff has been closed down. I see this talk is also a life of its own. It's moving along by itself, but I want to thank the contributors to this talk, which are listed here, including our startup company. The vision that we started on way back when, which I thought there was a timeline, was that we wanted to count every single photon that comes into the image sensor. And that was quite a paradigm shift from the way things have been done before. So the idea is that if you can count every photon as it comes in, then theoretically you can reconstruct the image from all these bits. So the vision was that we would have a billion specialized pixels on the chip, a billion, and we'll read them out at 1,000 frames per second. And every pixel is a specialized pixel that only can count a single photon. So we call that a jot, because we're going to use a lot of jots to make a pixel. Also, we want this whole chip running at 1,000 frames per second with a billion pixels to consume less than a watt of power. So this might seem like a lot of extra work compared to integrating a bucket of charge in a conventional CMOS image sensor. You're right. But then again, counting every visible photon is about as sensitive as one can get for photography and security and defense, space, etc. And it helps with small pixel versus full well capacity trade-off. And it also allows new capabilities in computational imaging, such as trading sensitive and resolution that can be scene dependent or attention dependent with different sensitivities and resolutions in different part of the image. Permits time delayed integration of multiple independent tracks in arbitrary directions as you reprocess that binary data cube accordingly. Also allows motion blur compensation for multiple targets, and also could allow high apparent SNR for very low photon flux. I'll show some examples of that coming up. So short timeline. This work started around 2004 or so when I was asked to write a chapter actually on what the future of image sensors might be. Unfortunately, I was working for a MEMS company. I was actually running a MEMS company at that time, so I didn't get a chance to work on it too much. I went to Samsung as a consultant in 2008. We did a small brief effort, but because of the financial meltdown, that project was terminated soon after it was started, even though I continued to work at Samsung. When I finally got to Dartmouth, took a couple years to really kick off an effort on at Dartmouth, and then been working over 5 or 6 years after that on this, and to the point where we actually got a device working, and my students were graduating, and so they decided they wanted to spin off a company, which is called GigaJot, which is in Pasadena, California, and they're continuing to work to this day as, and I'm a co-founder of that company. So I think everybody at in this meeting knows about Poisson process and photon arrival rates, but basically you've got the Poisson distribution, and which tells you what the probability of having k photons arrive in some interval, which depends upon h, the quanta exposure, the average arrival rate. So, but for these binary devices, we only care about two states of interest. One is that no photon arrived, that would be a 0. So that's just e to the minus h. And then also that that at least one arrived, which is more than 0, which would just be 1 minus the probability of 0. And we always talk about a ensemble of jots and looking at statistics that way. So the photo response of this type of sensor is really bit density of on the focal plane. It's not a linear response. It's goes as that 1 e to the minus 1 minus e to the minus h, and gives this curve here in blue, which compared to sort of a linear sensor gives you this very predictable overexposure latitude as a function of exposure. And that was kind of the first interesting things about this sensor, is that it, even if it's not linear, it is statistically well understood, and that means returning to the linear response is also quite straightforward. You're not worried about thresholds of devices or other weird, clever device constructs. It's just right inherent in the physics and statistics. So if you plot that same plot that I just showed on a density versus a log exposure curve, the linear part, which was down to the left, is kind of this upward shaped curve, and then it bends over in the overexposure part. You get this S-shaped curve. And just as a interesting thing, in 1890, Herder and Driffield were looking at film and plotted the density versus log exposure plot, and it's exactly the same curve. And the reason for that is that film grains are basically binary detectors, because they're either wash away or don't wash away when you develop the film. Now our approach to detecting single photons is not your normal approach. We didn't want to use avalanche multiplication for reasons I'll get into soon, but our approach was to use a very low capacitance as a sense node. So for example, if the voltage on a capacitor is the change in charge divided by the capacitance, then you could theoretically get a millivolt swing on that capacitor, voltage swing, from one electron if the capacitance was perhaps as small as 160 attofarads, 0.16 femtofarads. So in our device in the cartoon here, we have light comes in, generates photoelectrons, and then for some integration period, then we reset the sense node capacitance. We then measure the voltage on the capacitor using a correlated double sampling approach. Then we do charge transfer to that capacitor and measure the new voltage and take the difference of those two readings before and after. That's the correlated double sampling part. And by the way, just conversion gain is just defined as the volts per electron that we get on that sense node capacitance. A millivolt would be great, but typically these days we're around, let's say, 300 to 400 microvolts per electron. Now, if you take that same device and you look at what the, over many, many samples of that same device, as different photons come in with some average rate, let's say h equals 2 in this example, quanta exposure of 2, then without any additive noise, then the voltage output should be very quantized, corresponding to 0 electrons, 1 electron, 2, 3, 4, 5, etc., with amplitudes corresponding to the Poisson distribution. If we have some additive noise, as you can sort of shown there in the cartoon. Then these nice peaks actually wind up broadening due to the read noise, and you get the kind of blue-shaped distribution. If we add more noise, that's just 0.12 electrons RMS. If we add, say, 0.25 electrons, that's input referred read noise, we get much broader peaks. And in fact, by the time we get to 1 electron RMS, which sounds like pretty good read noise for a CMOS image sensor, you don't see any quantization anymore at all. That's the blue curve. So for our quantum image sensor, for a single bit device, we're just going to set a threshold on a comparator to the left of the black arrow at the bottom there. We'll call that 0. And to the right of the black arrow, we'll call that a digital 1. And so as you add noise, kind of if you go back to this point, if there's some noise like in the orange curve, then that means there's some chance that you have a false positive or false negative. So we can calculate the bit error rate for those things, and at 0.3 electrons RMS read noise, for example, then about 1 out of 20 bits is incorrect. But if you can reduce that read noise to 0.15, then it's dropped down very quickly to like 1 over 2,500 as for the bit error rate. So our target really is to get down to about 0.15 or lower electrons RMS, input referred read noise. It's good to know what the effect of the read noise is on the photon counting accuracy. So we have, on this plot, we've got quant exposure, log quant exposure on the horizontal axis, and counts, expected counts on the vertical axis. And we'd like a nice linear relationship between the quant exposure and the output count. But if you look at the 0.15 electron RMS curve, which follows a linear curve starting at the beginning, and by the time you move up towards 1 electron count, of course, it starts to saturate, as we talked about before. Now, so at higher noise levels really affects the you don't want. And even by 0.3 electrons RMS or something, your accuracy at low quant exposures is not so great. So again, 0.15 is a pretty good number to shoot for. Okay, so after thinking about single bit for a while, I realized, well, you know, we could have multiple bits. And the reason is, if I'm going to flash back here, you see that this curve histogram is well behaved even out to higher electron numbers. The read noise still, or the probability still touches down to 0 between the quantized values. So that means that there's, it's pretty easy to detect between 0 and 1. It's also just as easy to detect between 5 and 6 electrons. So we can start thinking about maybe putting multiple electrons, not a lot, but a few electrons anyway, into the well, and increase the capacity the device has for photon flux, as we can the device can still work even at a higher photon flux rate. So for a 2-bit multi-bit quiz, then we're going to have 3 comparators as shown by the black arrows at the bottom at these different values, and basically code the data as 0, 1, 2, or 3 or more electrons. I think I'm going to skip this curve, but you know, at some point you think about it, well, what if your full well grew to you know, multi-bit, but it was like 10 bits? That would be exactly the same as a CMOS image sensor, except with really low read noise, and that's correct. So in the limit for high bit depth, you're just back at a CMOS image sensor, although higher read noise. So lower photon counting accuracy once you get down to the noise floor. And then you can plot that same accuracy requirement for multi-bit as well. And in this case, I've also added in some experimental data as the points on these curves. You think that if you have a single bit device, then the dynamic range is very limited. I mean, wow, it's totally saturates when you just have a few electrons per pixel. But you can actually, we're reading at a very high frame rate, and you can use the electronic shutter inherent in the device, rolling shutter, to take multiple frames before you combine them. So that some frames have very low sensitivity, that's with a very short shutter, and others have maybe the full millisecond or something of integration time. Combine all those things, you can wind up still with a very decent dynamic range. So maybe 120 dB or something like that. I'm sorry. So just as an example of that, here's work that was done by GigaJot and Purdue University Professor Stanley Chan, where they're actually taking some very high dynamic range images by using his 3-bit multi-bit sensor. So I will let you peruse these slides later. They'll be shared, so you can take a look, but actually the image quality is actually quite good. So for our Pixel, we had to invent a new device that would be sensitive to a single photoelectron, and that's this pump gate jot device that myself, JJ Ma, and Donald Handagwa are co-inventors on. And this device is a little different than a normal CMOS device. We store the storage well, store the electron in the storage well below transfer gate. When we're ready for readout, we pulse the transfer gate that pulls the electron up to the surface. And then when we turn the transfer gate back off again, because of the way the surface is doped, the electron doesn't go back down into the storage well. It actually shoots off sideways into a floating diffusion sense amp. And that floating diffusion is purposely separated away from the transfer gate to make sure it has the lowest possible capacitance and the highest possible conversion gain. So recall what we expect to see. So if we test this pixel out, we get data like this. So this is for a histogram that's made by reading the same jot about 20,000 times, making a histogram of the output signal that we get. And this corresponds to about 0.175 electrons RMS read noise. For top left is for an average quantum exposure of 1, and the bottom right is for an average quantum exposure of 4. And we can see that it's very clearly quantized, and we can get the photon number well. In fact, that's worked so well that we actually used the Poisson statistics to fit the curve. And from that, we can get the read noise very accurately to within, easily to within 1/100th of an electron RMS, and also get the flux, average flux to almost a similar accuracy. And by the way, the peak spacing also tells you what the conversion gain has to be, of course. So this is just another example. This is with a quantum exposure of 8, just showing that we still see this quantization all the way out to 18, 19 electrons. Quantum efficiency on this backside illuminated device is quite good. This is a plot made by GigaJot, which shows it peaking at about 85 or 90%, somewhere around that range, over a fairly broad wavelength range. Sorry, this slide shows have a life of itself. And I think it can probably be further improved as well from here. I should mention that the device was made at TSMC in their CMOS image sensor fab line with a few implant modifications that we made, and of course some mask changes. Lag is also important. If you're talking about a single photoelectron, you want to make sure that that photoelectron doesn't get lost along the way, and lag is an important measurement to make, and this just proves that our lag is very, very low. We don't lose any electrons. Dark current is also very well behaved. It's at just about 0.07 electrons per second at room temperature. Has been measured by several groups now. pretty well behaved. And in fact, if you look at the histogram of the dark signal, you still see quantization in the output, even though this is for a lot of different pixels all summed together. The reason for the low dark current is the fact that we're storing this electron in the storage well that's deep below the surface and isolated from a lot of surface-related defects in the silicon. Okay, if we cool the device, we can further improve the noise. This is actually the left side is a scattergram of a lot of different jots in the same array that are measured, and we calculate the conversion gain for each one individually, and we also calculate the read noise, or to measure the read noise for each one, and plot it on this scattergram. And the red curves are at room temperature, the red dots are room temperature, and the blue dots are at lower temperature, minus 70 C. First thing is that the scatter is significant, and the second is that, but not that bad, because we're only trying to count single bits or a few bits data, but also that generally the conversion gain increases a little bit when it gets cold, and also the read noise drops. So on the right side lower, you see that the just a slice of the distribution of read noise shows that at minus 70 C anyway, some devices are down around 0.17 electrons RMS, and a lot are below 0.2, and then a tail that goes up. Frankly, that sharp cliff at about 0.17 is still a mystery to us. We're not sure exactly what causes that. Seems counterintuitive. We think we'd have a more symmetric sort of distribution. Certainly, the noise in the first transistor now is quite critical, and the source follower. That's true for most CMOS image sensors anyway. And so I've just shown the schematic of the pixel along with kind of a cross section of that source follower MOSFET, and MOSFETs tend to have a lot of 1/f noise, which is sort of cartoon-wise shown on the right. Then it kind of goes as 1 over the gate area, which is bad news for us, because in order to reduce the capacitance, we have to make the gate as small as possible so we get the highest possible conversion gain, so that we can overcome the noise floor. But in the process of doing that, we're actually increasing the noise floor at the same time because of the 1/f noise. So that is a unfortunate trade-off in life. In the last year or two, perhaps longer, we've been trying to understand the origin of that 1/f noise, because that's obviously key to further improving the bit error rate, even though it's pretty good right now. My student Wei Deng has been looking at this for a while, and on the I guess there are a couple different models for 1/f noise. One's a mobility fluctuation model that was proposed by Hooge. McWhorter had a number fluctuation model where the number of carriers are fluctuating due to trapping and interface traps. And that's pretty consistent with what's also come to be known as a random telegraph signal, or random telegraph noise, RTN. And a histogram of the RTN, random telegraph noise signal, is shown here on the right side. And what that's saying is that most of the time you get, relatively speaking, 0 signal out, but then you get an electron trapped or detrapped, and the voltage will shift to the left or to the right, depending upon where it was starting from for that particular cycle. And so we see these 2 clear lobes on the left and the right, and that represents that single electron trap somewhere in the channel that's causing a disturbance to the current. But if we look at that signal a little more closely, we see that for our device, which is also supposed to be sensitive to a single electron, that corresponds to 13 electrons of input referred signal, which is huge. That means we have a device that is very sensitive to random telegraph noise, also with a huge signal. And most of the time we don't see that signal. So only about 2% of our devices show this random telegraph noise. The rest don't, which is pretty consistent with the number of traps we expect in that gate area and that size. Further, if you look at this curve closely, you'll see that each of those lobes in the center peak also have a broadening. And that's what we're interested in, is that residual 1/f noise, which is interesting because people normally like to blame 1/f noise on these interface traps and trapping charge. And they say, oh, well, there's an ensemble of traps charging and discharging at different energies, different frequencies. You add them all up together, you get 1/f noise. Here we see that even one trap is a really clear signal, and yet in here is still this extra 1/f noise that is not easily explained by trapping mechanisms. So we're still studying this and trying to understand what's going on. Skip that slide. And again, these slides will be later, so you can look at this some more. This is just kind of questions of the day of what we're trying to look at. Back to our device, we built a 20 megapixel device. It's 20 different 1 megapixel arrays on one chip. So is this 1 megapixel quantum image sensor or 20 meg? I'm not sure. I guess let's call it 20 meg because it sounds better. We built it in the TSMC CMOS backside illuminator process, which is a 45 nanometer, 65 nanometer, 2-layer stacking process. We came up with this new readout architecture, which we call cluster parallel, where every cluster of JOTs has its own complete self-contained readout circuit. And that makes scaling pretty easy for scaling up to ultimately gigajot, I guess. But we did a lot of variations, different pixel designs, and also analog output devices and single bit digital devices where the quantizers in the readout circuit. Pixel pitch is 1.1 microns, and looked at a lot of different things, as I said, including a JFET circuit, which I'm not reporting today. So results from this device, the input referred noise is about 0.22 electrons RMS on average. The dart count rate at room temperature, as I said before, is about 0.07 hertz, if you want to think about dart count rate, which is quite low. Of course, it's even slower when it's cooled. And this is read out at 1,040 frames per second, single bit, and the total power, including the pads for this megapixel array, is 17.6 milliwatts, which is also, well, practically amazing, okay, that you can do that for 17.6 milliwatts. So that's pretty cool. Then we built a camera, and I must say that a lot of this work that I'm reporting right now is done by J.J. Ma and Soleil Masoudian as PhD students at Dartmouth. But they're able to take a picture of a picture and basically realize large parts of the dream that I presented at the beginning of being able to recreate images from this binary data. So GigaJot was spun off by Soleil and JJ in 2017 and myself, thinking that this technology would be very good for low light, high resolution imaging, and photon number resolving systems. So it's security, low light, Internet of Things, biological imaging, astronomy, quantum cryptography, probably, photography, and cinematography down the road. So just an example, is an image taken at an average of exposure of less than 1 photoelectron per pixel on average. So the image on the left is the raw image, and that's with a 3-bit quiz. So 0, 1, 2, 3, 4, 5, 6, or 7 photoelectrons. Even in the aggregate of across the whole array, you can still see a pretty obvious quantization on the lower left histogram. Then you can, up above in the center, clean it up a little bit by using a 2 by 2 by 2 cubicle sum, which improves the image quite a bit. But then working with Stanley Chan's group at Purdue on further denoising, or much more sophisticated denoising algorithms, You can see you can actually get an amazingly clear image at less than 1 electron per pixel average illumination. So if you ever looked at low light images, that should blow your socks off, because it's an amazingly clear image, as we hoped would happen. Okay, I'm going to just change topics here just for a second and just talk about SPADs for a moment, because certainly another candidate for the Pixel is single photon avalanche detector device. And I don't want to give a whole talk about SPADs for sure, but here's status in 2016. Dart count rate, as you see in the lower right, is several hundred counts per second at the room temperature, on average 24 micron pixel pitch for a 512 by 128 array. And of course, the idea in a SPAD is that you put a high enough electric field across the PN junction, you can result in avalanche multiplication and breakdown, which is self-quenching for that device. So one single photoelectron can trigger the avalanche. And that gives you kind of a binary output. The device is either latched up or it's not, I shouldn't say latched up, but either triggered or not triggered. So if you're thinking about building a gigajoule array, 24 micron pixels is not very satisfactory. You recall at the same time we were already building 1.1 micron pixels for the CMOS type quiz. Also, the high electric field leads to a lot of manufacturing issues, pixel size scaling issues and manufacturing yield issues, which are also problematic. These are just summarized here. On the other hand, I will say that if you want to do time resolved photon detection, it's impossible to beat a SPAD. SPADs are fantastic. So it's just relative to building the quantum image sensor vision that presented earlier that SPADs have an issue. More recently, Canon built a SPAD type quiz. It just came out this month in Optica. So now they're down to 9.4 micron pitch. It's actually, well, this is like 2 different half megapixel arrays or 1 megapixel. So either they did a megapixel and we did 20 megapixels, or we did 1 megapixel and they did half a megapixel, depending upon what you're trying to brag about, I guess. And then the data is over here on the right side. But definitely good improvement, especially in the dart count rate, has come down to single digits. So that naturally leads one to think about comparing the CMOS image sensor quiz to the SPAD quiz, SIS quiz to SPAD quiz. So here's a table, and you see that I put actual to date for SIS quiz and SPAD quiz, and also where it might be in 3 years. And it's just a wild ass guess, really, on where we'll be. Array size, probably SIS quiz will reach more than 100 megapixels in 3 years. SPAD quiz probably move up to 1 to 10 megapixel range. The size, die size, you can see is quite different, almost 10 times larger for the SPAD quiz and lower resolution. Fill factor on the SIS quiz is very high because of the way that device is built. SPAD quiz is, depending upon whether they go BSI or not, still about 13% maybe. Photon detection efficiency is also a problem. SIS quiz is about 70%, whereas the SPAD quiz is reported to be about 3.6%, which I assume will improve. On the slightly negative side, the frame rate for the SIS quiz is 1,000 frames per second, whereas the SPAD is, they reported 24,000 frames per second. Although, to be honest, we can run the SIS quiz 5 to 10 times faster if we wanted to burn 5 to 10 times as much power. You'll recall that we're also constraining the power in the initial designs as part of that vision. Read noise is better in the SPAD quiz, of course. If you, SPADs also are not very good at multi-bit devices. And then if you calculate the flux capacity, especially if you're worried about dynamic range, SIS quiz is about 0.8 kilo electrons per second per square micron. And the SPAD quiz, even though it's at 24,000 frames per second, is only 0.3 kilo electrons per second per square micron because of the larger pixel size. Power is also important. We're like 20 milliwatts for 1 bit, and they were at like 535 milliwatts for 1 bit. It's another big difference. So far, they haven't done color yet, so we've done color. Here's an example of color. It's not like world's greatest color, that's for sure, but here we're doing this an average light intensity of about 0.7 electrons, 0.7 photoelectrons per pixel, and trying to extract the color image from that. And the left side of this slide is a standard color pipeline, and the right side is a neural network based approach done at Gigajot. Stanley Chan recently published a very nice paper on image classification in the dark using quiz devices, and finding that they can do very, very good recognition of different things in the scene at very, very low light levels with a quiz compared to CIS, and it's all has to do with read noise. And of course, that'd be true for SIS quiz as well as for SPAD quiz. That motion flow and motion correction thing that I was proposed back in 2010 or so, I guess, has been realized nicely, most recently by Gupta and his other folks in Wisconsin, and then also Eduardo in EPFL. And they're just showing that you can move the camera around and then take that giant bit cube and parse out what's moving, what shouldn't move, and come up with a pretty clear image in the end. So it worked. So just to wrap up here, almost precisely on time, this is my pictures of some of the people in my group at Dartmouth, and this is a composite image, I should say. They weren't all there at the same time, and so I photoshopped different people in at different times. So thanks to all their hard work, and thanks to our collaborators, Stanley Chan, as I mentioned before, but of course Gigajot out in Pasadena, California now. So I believe that is the end. Yes, it is. So thank you.
Okay, thank you, Eric. I'll clap on behalf of everyone who's muted. Thanks for an excellent and very clear talk. We have time for questions, and I'll take a look at the chat window here, and you could do the same, Eric. If you see a question, feel free to answer it. I have a few questions, so I will copy and paste my questions, one of which I think you already answered, but I'll paste them anyway. And
you should just read them to me, because at the moment I am trying to figure out how to see that chat window. Yes.
Sure, that's fine.
Oh,
There's a floating menu bar, I think, that should have the word chat in it.
I got it now. Okay.
The first one I think you answered.
Let's see. So what are your plans to scale to bigger formats? Yeah, can I answer that? I think there's a good chance we'll see 100 megapixel arrays before long. Let's see, if you make bigger pixels, with performance suffer, e.g. read noise? I don't expect so, because it's the size of the sense node, not the size of the photoelectron collecting area that counts. So we still have to transfer the charge from the larger collection area to the small sense node, but it shouldn't affect the read noise much. Speed limit for single pixel is an excellent question. As I said, we right now the read cycle takes about a microsecond, and the frame rate is about 1,000 frames per second. But it has a lot to do with power and a few other things. So I don't think we'll ever get to the speed of a SPAD that's got sort of nanosecond timing, but it's possible. Maybe 10 nanoseconds we could do, which is good for a lot of ranging applications. Just affects the accuracy of the range a little bit, or resolution, I should say. And why does noise go down with temperature? Um, well, that's an excellent question. If we did some modeling of those different noise models, the Hooge and the McWhorter models, and they all have a temperature dependence. And I kind of skipped over that slide pretty quickly, but the model that Wei Deng did seems to agree pretty well with um, the temperature dependence seems to agree pretty well with one of those models, which is the McWhorter model. Oh, sorry, Hooge model. Got to get that right. Sorry, I should go back. I can't. But you know what? I don't feel like we've gotten to the root cause of the noise yet, and I don't really believe the Hooge model or the McWhorter model at this moment. Too many things are don't make sense to me. So even though we were able to fit it, okay, I'm not sure that those models are really the true models of what's causing the residual 1 RF noise in these devices. So it's a less exciting thing to study, I suppose, compared to building devices and large arrays and things like that people have never done before. But sometimes it's important to do that slow, methodical study to understand the root causes of things. And so that's what we're engaged with now.
Okay, thanks for the answers. Do we have any other questions? I have many questions, but I'll not ask any more. I think I already have 4. So
yeah, you're a collaborator, so you get lots of time to ask questions.
yeah.
Unless you want to embarrass me, that's okay. Go ahead and ask away.
Well, I don't know if this is a question, but for the James Webb Space Telescope Detector Development Project, we were able to freeze out the traps, just like you did. And as we went to lower and lower temperature down to 40 Kelvin, we were able to get trap lifetimes of hours. And so you would see it pop between, 2 different numbers in ADU. And the interesting thing is, as long as you were reading, you were doing the CDS while it was stuck in one state, then
Right.
you get rid of any effect whatsoever.
That's right.
Which is just what you've shown. And at higher temperatures, the lifetimes were so short that it was just like the blur that you see on an oscilloscope when you try to zoom into the scale. It was just always popping much more quickly than we were sampling.
Well, you're going to be testing our devices at low temperature before too long at RIT. So looking forward to seeing if that is true for the quiz devices at very low temperature too.
So let's go ahead and move on. There are no more questions. Eric, thank you very much. And we're going to move on to a poster presentation. And I'll go ahead and close off this recording. And then I'll